to talk about, review the exoplanet atmosphere theory. And what I thought I would focus on, rather than looking back so much, is rather to pick a few current topics for exoplanet atmosphere theory and talk about how we might, as a community, do them better in the future, or maybe shift our focus a little bit, both for the observers and the theorists trying to interpret the data. So it's sort of my perspective on where we should be going, or the view from, the theory view from 2020. As I was putting this talk together, I remembered back in the 1990s, I wrote a conference proceeding over what I thought the topics for exoplanet atmosphere theory would be in the future. And my take back in 1998 was that the interesting things would be disequilibrium chemistry, stratospheric heating, clouds and photochemical hazes, and the understanding the thermal profile of planets and looking for any deep radiative zones. And on the right is a figure from that paper where I think it's the first irradiated exoplanet models, where there was little small inverted temperature profiles for some of the radial velocity planets. Of course, at the time we were thinking about direct imaging and not transit. But I thought I'd use these ideas, since this is what is interesting about giant planet atmospheres in general, is to go through these and think, where are we today in these topics, and where should we be going in the future? Because of course the field has blossomed far beyond what anyone could have ever have expected, as Jane so ably went through where we are with the observations. So I'm going to focus on, looking forward, focus on giant planet atmospheres, just to narrow the range of topics. This is not at all to disrespect the terrestrial planet atmospheres, but it's just where the field is today in terms of the data. I'm going to pull some examples from the solar system and brown dwarf theory. And I want to stress these are my opinions on a few of these things. If you disagree, let me know, and let's talk about it in the chat. In fact, when Kevin invited me to give this talk, he said, well, hey, you could be controversial a little bit. So I'm going to take him up on that and express some strong opinions on a couple of things. These are, again, my opinions, although other people have said the same things. And I'm just kind of collecting some of these issues together here. If I happen to mention something where I think we need to do better that you've worked on, please don't be offended. Everything that I criticize, I myself have done, and I'm on plenty of papers that do these. More, it's looking forward, looking to the future. How might we shift our focus on some of these topics? And some groups have already moved on and are doing these things that I'm talking about. So it's more of a generally, where should we be going and what are some of the right things to be doing? So with all of that said, let's talk about these four topics, and we'll start with the first one on the atmospheric abundances and disequilibrium chemistry. As Jane has already said, there's been remarkable progress in measuring atmospheric abundances and detecting all kinds of species. I think the flagship thing for the last few years has been some of the atoms, including the detection of helium. On the right is an example of interpreting these spectra. This is GJ436b, which seems to be, it's a hot Neptune, and it seems to be highly enriched over solar abundances. This is by analysis by Marley et al. And the important thing I want to point out is that this work included two things. It included retrieval study and also model fits, grid model fits. And as I'm going to come back to, I think we really need to be doing both of these things, using the self-consistent forward models and retrieval models to get our hands around what's going on in exoplanet atmospheres. And of course, there's been hints of lots of other new species. I think some things where we can do better is that when people present abundances, it's not always clear what exactly they're referring to, or when we talk about enhancements, what is really gone into the estimate. Let me give one example. When the silicates and refractory condensates form, that sucks up about 20% of the oxygen. If you observe a cooler atmosphere, the oxygen abundance you're looking at has been reduced by the amount that's gone into the grains. But it's not always clear when people report abundances is if that's been accounted for or not. Likewise, when we compare to equilibrium abundances, does that mean true chemical equilibrium, as you might get from the CEA code, or has it been adjusted for rainout? So these are things we can get a little bit more clarity on. Also, I just want to mention one of my personal pet peeves is when the solar system metallicity mass relationship really shouldn't be extrapolated out to subsolar abundances. I don't think that's real meaningful in terms of what the solar system in and of itself is telling us. And the plot on the right from Arcangeli et al. Does, in fact, level it off at 1 times solar, and I think that might be a better approach. So all of these abundances we are getting from retrievals. And as I've said, I think retrievals are most informative when we pair them with self-consistent forward models. And the reason is that because when you retrieve a temperature pressure profile, there's no guarantee that the profile that you've retrieved is in, say, radiative equilibrium. And the radiative time constant for many of these atmospheres is very short. So if you had a particular profile and you let it go, sometimes it would collapse back to something else very rapidly. And so I always think we need to compare both what the retrieval is saying and what the forward model gives us. And it's the combination of the two that provides insight into what's happening in the atmosphere. On the right is just an example from brown dwarfs from Ben Birmingham's work, where the shaded region is a retrieved temperature profile for a cloudy L dwarf. And the forward models are quite different. As the yellow arrow shows, the temperatures are hundreds of Kelvin cooler. So something is changing the profile that we don't understand. And this is an example of saying the theory is missing something. What are we missing? And we learn something from that. And so I just encourage people to always try to include both. Sometimes, in thinking about the chemistry, and we often see the plots of the chemistry, departures of retrieved chemistry profiles from chemical equilibrium are explained by invoking chemical disequilibrium. And in fact, if you look in the ADS, there's hundreds of papers on exoplanet atmosphere chemical disequilibrium. It's a major theme of exoplanet atmosphere theory. And just to remind you what that means, the plot on the right shows an atmosphere profile, and the down is to the right. And as we move to the left, when the chemical mixing timescale, shown by the dashed line, is equal to the chemical equilibrium timescale, shown by the solid line, we say the atmosphere, in this case for carbon monoxide, the abundance is quenched. So the carbon monoxide is then mixed up higher in the atmosphere, and we see a couple of orders of magnitude more carbon monoxide than we otherwise would. And this is interesting, and a lot of work has gone into this. But I really feel that the exoplanet community as a whole is getting too hung up on disequilibrium chemistry. And so my first sort of controversial point is that disequilibrium chemistry alone is not very interesting anymore. I'm specifically talking about giant planet atmospheres. Of course, I'm not talking about finding life in a terrestrial planet. The reason I say this is the basic idea has been understood since the 1970s in Jupiter's atmosphere. Immediately after the first brown dwarf was discovered, Fegley and Lauders predicted that disequilibrium chemistry would be found in brown dwarfs. And the very next year, Knoll et al. Indeed found that and confirmed the CO methane disequilibrium. It's not surprising. It's a basic part of giant planets. It's produced by both winds and vertical mixing. And so I think we don't want to stop any longer at just saying, wow, there's disequilibrium chemistry, that's useful. Instead, I think what we need to do is move on to really focus on what we can do with disequilibrium chemistry. This is both what the theorists and the observers can do to try to do better disequilibrium. For example, what are the mixing timescales? Let's measure the mixing timescales. Can we invert for, instead of just chemical abundances, can we solve for the eddy mixing coefficient through the atmosphere? Does the overall picture make sense? And I want to give an example of this from Brittany Miles et al. I'm on this paper, but she did all of the work. She's done an amazing job with this. But what she did was look at brown dwarf profiles, compare them, and then use her own data from M-band for very cool brown dwarfs, measure the carbon monoxide abundance, and then figure out what the eddy mixing coefficient in the atmosphere is as a function of temperature. So now we have a map through the cool brown dwarfs that shows that eddy mixing seems to reach a minimum around 500 or 600 degrees and then ramps back up as we go to cool temperatures. This is the kind of information that's really interesting, and I think this is where we need to be going in the future for exoplanet atmosphere theory, is taking everything to this next level. What can we learn from the disequilibrium? With that said, let's go on to the second topic, which is hot stratospheres. Hot stratospheres are very common in the solar system, where you see this temperature inversion. And the heating in the stratospheres in the solar system is typically from disequilibrium chemistry or photochemistry. For example, ozone in the Earth's atmosphere produces the temperature inversion. It was predicted for hot Jupiters from TIO or VO absorption to visible way back by Hubany et al. In 2003. And the idea was that if TIO does not condense in the atmosphere, you have this very good visible absorber that's pumping energy into the atmosphere heats up, and we have a thermal inversion. And much of the theme of the 2000s was using Spitzer data to find inversions and to go look for these absorbers. Fortney et al. In 2007 suggested we might even have two classes of hot Jupiter atmospheres, those with and without the TIO and with and without the inversions. And I think what's been interesting to me is that there really has only been solid evidence for inversions in the ultra-hot Jupiters. We heard just yesterday from Yan et al. Showing very clear evidence in iron lines. But for the run-of-the-mill hot Jupiters, there really hasn't been great evidence that these inversions really are there, even though there has been evidence for TIO in optical transmission spectra, like we have here from Sadgati et al. 2017. People have also suggested that other absorbers could be important. Some of the refractory oxides, atomic species, even UV absorbers like HS or CO. It's hard to heat them up from the UV because there sometimes isn't that much flux. But there's been, I think, a lot of focus on what are the heating mechanisms. Can we go find these absorbers? Can we go find evidence for the inversions? And I think that is interesting. But it's really only half the story. To have a thermal inversion, you need both an input of energy, but you also need inefficient cooling. If the atmosphere can radiate away the energy that's absorbed, then it doesn't necessarily heat up enough to give you an inversion. On the right, and then again in the solar system, it's often methane and some of the photochemical hydrocarbons are important coolants. On the right, back on the solar system profiles, you'll notice that from Jupiter to Neptune, it's about 150 Kelvin difference. But if you go to the top of the atmosphere, the temperatures are much closer. There's much more similar temperatures. And the reason is that all of these atmospheres have a thermostat, and that thermostat is methane. This is a real image of methane emission from Jupiter's atmosphere, the 7.8 micron methane band. And you're radiating away energy absorbed in Jupiter's stratosphere. One way you can think about this is this figure looking at Uranus's atmosphere. The top is a Planck function for maybe when you're at 80 or 90 Kelvin. And the Planck function, it's so cold, the Planck function overlaps the pressure-induced opacity of hydrogen. So the emitter that's emitting away to space is out at 25, 50 microns. And the histogram pointing downward shows you what wavelengths a layer in the atmosphere is cooling out. But if we start putting energy into that layer and heat it up, we only have to heat it up a little bit, up to about 125, 130 Kelvin, so that the Planck function just starts to overlap with the 7.8 micron methane band. That band can now radiate away and can start cooling the atmosphere. This happens in all the giant planet atmospheres. And as soon as the Planck function gets warm enough, the thermostat clicks on and the atmosphere starts cooling. And I think that for the future of thinking about inverted stratospheres for exoplanets, we want to really understand not just the heating side of the equation, but also the cooling side. There's a really nice paper by Parmentier in 2018 that's doing that for the very hot Jupiters. And they show that for those objects, the water dissociation control is that thermostat, because water is so good at radiating and cooling the atmosphere that when you get rid of the water, when H2 gets so hot that H2O dissociates, you can't radiate by the water. That's when the atmosphere flips over. Nice figure from Baxter et al. From this year shows that on the right. We don't have an inverted stratosphere until it gets so hot we lose the water and it heats way up. Likewise, it's been suggested that high C to O ratios would do the same thing. You have more C, you have less water, and likewise could produce inverted stratospheres. I think with JWST, there's going to be an opportunity to really see what the coolants are, and we may be surprised in the mid-infrared at what's emitting. And so as a topic for the future, looking at stratospheric inversions, the stratospheric energy balance, thinking both about the cooling and the heating, I think will be important. Let's talk about clouds for a little bit. Of course, it goes without saying, clouds are present in every substantial solar system atmosphere. They play a crucial role in reflectivity and energy balance. There's hundreds and hundreds of papers in the ADS on exoplanet clouds. For the terrestrial side to draw inspiration from, it's a deep and complex literature. And so I think a fundamental problem for exoplanets is finding what is the right degree of complexity for all the theoretical modeling and for interpreting and for inversions. What's the right complexity to understand clouds? And I think we don't know yet. I think there's been a lot of really good work trying to poke at this, and I still feel like we don't really have the right answer yet. In the transiting clouds, typically we have, it's the typical framework has been where there's a scattering haze overlying an opaque cloud deck, which is semi-infinite and goes down. And as Jane showed, we have a common thing is to look for the slope, the Rayleigh scattering slope in the blue, and see how steep that slope is. Sometimes the slope comes out to be steeper than a Rayleigh slope. And a lot of times we say, well, there must be some haze or some aerosols up there that's giving us the steep slope. But there hasn't been as much work on exactly what are the properties of this haze, what exactly is giving us this steep slope. That's why I really liked a paper this year from Ono and Kawashima, where they tried to really understand what is causing, what are the properties this haze has to have in order to give us this steep slope. On the right figure shows for some multiple hot Jupiters, the slope into the blue, and you see that some of them are quite steep. So how do you get down there steeper than the Rayleigh slope? And what they did is look at haze production rates and eddy mixing in the atmosphere to see what combination of haze production rates and eddy mixing coefficients would be sufficient to mix the hazes up. If you don't have any haze, then you just get a Rayleigh slope, like in the left of the bottom right figure. If you have lots and lots of haze production, you're essentially moving that cloud up higher, giving you a flat spectrum at a higher transit radius. But then there's these intermediate cases where you have some haze production, it's the right particle size, and then you can get this very strong slope into the blue. And I think that this kind of work, trying to really understand what are the particle properties. Are there fractal particles? Do we need to think of Lacey aggregates, for example, for producing this, is the direction we're going to see a lot of work from in the future. And you might kind of encapsulate all of this in saying we really need to think about clouds not as flat gray slabs, but really think about the particle properties and the mean scattering effects. This is just a canonical figure from Van de Hulst looking at the scattering efficiency as a function of the particle size parameter. So longer wavelengths go to the left. And the characteristics of how the light interacts with the particles, of course, depends on the width of the particle size distribution, here shown by the little b, and the imaginary and real indices of refraction. And of course, the interesting thing is in real particles, if you have a distribution of particles, if you go to longer wavelengths, moving left on this plot, eventually the particles in essence disappear. They don't scatter as well. And so that's an example of a me-scattering effect that we can look for in the future. Bahadinia et al. 2016 said that if we don't really have a semi-infinite cloud, if clouds have a cloud deck and a top to them, then as we go to longer and longer wavelengths for transit observations, we should be able to see through the bottom of the cloud, which would produce a step in the transit radius as a function of wavelength curve. Hannah Wakeford has also been looking at the vibrational modes that you can get from the refractory condensates or from the silicates. And this, of course, is something that people are going to be looking for with JWST. But we really need to think carefully about what all the size effects are from size distribution varying through the atmosphere. How do we model that? How do we really extract the information we want to get about the clouds from the observations we're going to actually get? I want to plug, there's a nice poster by Jake Taylor looking at some of these issues from thermal scattering from eclipse observations you should take a look at. So coming back to the theme of model complexity and what do we retrieve, highly schematic clouds are right in some situations. Try to be a little bit more complicated. We want to have a simple cloud model. Our old Ackerman and Marley cloud is now open source in Python from Natasha Batala. You can get it from her website. Cloud microphysics, like the Karma models or Christian Helling's group. Is that the right approach? But it takes a lot longer to run. Maybe we should be retrieving on single scattering albedo and then work backwards to figure out what the clouds are actually made of. And Jake Taylor's poster also talks about that. So I don't know the answer, but I think we all collectively need to think more carefully about what are the right things to retrieve. And Joanna Barstow has been thinking about these same things and has a really nice poster on this very topic you should look at. As an example of complexity being good, Peter Gao gave a talk yesterday talking about using karma to account for both silicate cloud formation and photochemical haze, doing all the microphysics and showing if you account for everything all together in a complicated way, karma seems to predict trends in water band depths as a function of effective temperature that agree with what's going on. So it's not to say complexity is always wrong, because it isn't. Sometimes you need it, and here's a great example. I think there's an underutilized effort to use the brown dwarfs. There's outstanding brown dwarf spectral libraries, there's cloudy brown dwarfs, there's low gravity brown dwarfs. The figure on the right, there's the data is in black, cloudy brown dwarf model in red, clear in blue. What's the right model for observing those? Eileen Gonzalez, who just defended her PhD last week, has a nice figure comparing directly imaged planets, gravities, and effective temperatures to field objects. And there's plenty of field objects, young, low mass field objects that look a lot like the directly imaged planets. And we should be using those more to refine our methods. And Joanna Voss has a great poster on variability of the directly imaged planets and what can we learn from variability. And I think that's, again, something where there's great synergy with the brown dwarfs to know what the variability is telling us. Also, there's been great progress in including clouds in the GCMs. Previously, the clouds in GCMs have been post-processed, where you run the GCMs and then turn on the clouds at the end. A number of papers, here's just two of them, Roman and Rauscher and Lines et al., are now including clouds as the GCM runs and including the radiative feedback, and they find that the answers they get are different. On the left, the top two panels include clouds in the GCM calculation compared to post-processed clouds on the bottom. So a problem that then this arises is, how do we describe clouds in the GCMs? What's the right level of complexity? And I think there's a lot to be done with that and to understand more. Let me briefly end with thermal profiles, understanding what's going on. Traditionally, we haven't thought too much about the deep interior, except worry about whether or not we're in a cold trap. That's starting to really matter. WASP 121b being an example where there's detection of magnesium and iron escaping. So there's no question is, do we see a cloud? Do we not see a cloud? We actually see refractory species in the exosphere. So you know they're not cold trapped. And so in order for that to be the case, you really have to have a high internal heat flux. And this planet is inflated. So now we can start to connect perhaps a measure of what the internal heat flux is to the actual inflation of the planet. And so that's an interesting direction that a lot more can be done with the modeling, I think, in the future. And finally, Jonathan Fortney has been thinking about these same issues uh, in the context of cool or medium warm, lower mass planets. And as they cool off, their temperature profile, their deep atmosphere can transition from where carbon monoxide is abundant to where methane is abundant. And depending on what the eddy mixing is through the atmosphere, he finds that it may turn out, surprisingly, that for low mass planets, cool low mass planets, methane shows up very late, perhaps as late as 400 Kelvin, whereas in the brown dwarfs, we see it much hotter at around 1200 Kelvin. So again, that's using the atmospheric abundances to infer mixing and what's going on in the deep atmosphere. There's also a poster by Malaveradicki et al. That looks also at these issues of where's the methane going, what's going on with the atmospheric CO. So in conclusion, these are sort of what I think are some of the themes for exoplanet atmospheres, the view from 2020. What will be interesting in the next decade, many things we don't even predict today. I think some of these long-running themes, disequilibrium chemistry, stratospheric heating, clouds, and thermal profile, there's a lot more we can learn, but we have to up our game and start thinking more about the planets as 3D complicated worlds and what these things are telling us. And so I'll stop there and take any questions. Thank you.
Thank you very much, Mark.